Hello everyone. Today we're going to talk about Physics 253, Week 9, problem number 29.17. In this problem, we are tasked with calculating the magnetic dipole moment as well as the magnetic field strength of a um, magnetically charged ring. So we'll be kind of talking about magnetic dipoles as well as how to kind of solve an equation involving these loops. So um, in this problem, uh, we're going over a lot of the ideas in chapter 29.5 of the textbook titled Magnetic Dipoles. And I've gone ahead and recreated one of the drawings in that chapter because I thought it would be helpful for our discussion of the problem. So here we have our ring right here, and um, although this is a magnetic field lines of a ring, since it is a superconductor in this case, it would look a little different. Since superconductivity is defined as a a scenario when electric resistance vanishes and magnetic flux fields are expelled from the material, um, we would have essentially uh, the field lines would be able to travel through the material and not just circle around it, like in this case. But although it is a superconductor, and although that we will be differing a little bit from this drawing here, we can still use the equation for the magnetic field of a magnetic field strength of a loop defined in chapter 29.5. In this chapter, we take a look at the magnetic dipole moment. This is defined as this mu right here. It is and this is area, not amperes. This is area times the current. Um, and we also have the area of our disks or our loops here as pi r squared. So um, in our case, we can go ahead for solving part A, we can go ahead and rewrite our equation for the magnetic dipole moment to include our um, diameter given here as well as our current in amperes given here. So we can just go ahead and plug straight in. We're going to have to convert millimeters to meters, but um, once we do this, we can get the magnetic dipole moment in ampere meters squared as the problem asks. So in the second part of the problem, as I mentioned, we're going to be using the equation given in um, 29.5. This equation is taking our vacuum permittivity as well as our magnetic moment, or I guess parts of our magnetic moment equation. Yeah, it'll give us the on-axis magnetic field. This is different. This is a different equation than um, some of the other magnetic field strengths because we're talking on axis, meaning that the magnetic field strength is going through the same axis, or magnetic field is going through the same axis as opposed to, something funky, just anything else really. But in our case, it applies, even though it is a superconductor. Um, so we can just go ahead and plug straight in. We have our vacuum permittivity in hertz per meter, and we can just plug in and solve for the equation. This on-axis magnetic field strength, I don't think it's something that we'll see too often, although it can be derived from other magnetic field strength equations that we use in this chapter. Um, so uh, or I guess we can derive other, excuse me, we can derive other magnetic field strength equations from this equation. Um, Specifically, kind of making assumptions using this denominator right here. Um, but in our case, this z right here, this z is going to be our uh, distance right here. And since it's on axis, this distance is going to be whatever, 4.6 centimeters away. And again, we have to convert this to meters here, and then we're free to just plug into this equation, and we're left with 3.7 times 10 to the negative 7 Tesla as our answer for the field strength. So thank you guys very much for watching. I hope you found this video helpful, and have a great rest of your week.